Topic is the memory of cars. Page 7, 2195866, AML, resection. Topics present in the slideshow are introduction, storage and memory, devices for automobiles, vehicular storage and memory applications, log diagram, and summary. First, my topic is about introduction. Introduction. Automobiles are steadily becoming rolling application platforms that reduce reduce computing power, networking, and communication capabilities with other cars, and the cloud, as well as with data memory and storage. Okay. Let's look at the requirements for memory and digital storage in automobile entertainment and navigation systems, including expectations for cars with driver assisted features and autonomous driving. The evaluation of memory and storage technology is a key element in creating the deep learning capabilities and rich media that are required for the car of tomorrow. Here you can see this car event recorder, anti-pitch window trap, airbags, globing control, odometer, electric brakes, racing engine management, transmission control, tachograph, something, etc. And the next topic in this slide is storage and memory devices for automobiles. Electrical system and electronics are about 40% of the value of a modern internal combustion vehicle. In an electric or hybrid vehicle, this can be as high as 75%. Electronic systems in automobiles depend on digital memory and storage to hold information that the automobile systems need to fulfill their functions. Various types of memory and storage devices are used in modern automobiles to keep bits used for entertainment, telematics, and navigation. Storage and memory device will also serve important roles in the next generation of partially autonomous driving systems. Figure 1 shows some of the electronic systems that use memory or storage in modern automobile. Memory used in automobiles include electrically erasable, programmable, read-only memory, NOR, and NAND flash memory, as well as long-term storage devices such as hard disk drivers, storage, and solid-state drivers. Future memories may include technologies such as magnetic random access memories that called as MRAM, resistive RAM RRAM, or phase change RAM PRAM. Let's look at some of these storage technologies. Although flash memory is common in applications such as for automobiles, where ruggedness is key, hard disk storage is a lot of expensive. HDDs store information on the magnetic surface of the rotating disk. There are smaller form factor 2.5 IN Rugged HDDs that are specially designed for the intense environmental conditions that automobiles experience. Toshiba storage products business unit makes a line of HDDs that are geared toward the automobile market. The Toshiba's MQ01AA D032C is 320 GB single platter serial attachment SATA means single platter serial attachment SATA auto HDD with rotation rate of 4200 R per minute and with an internal transfer rate of up to 976 Mbps per second and an average seek time of 12 m. These drivers are optimized to handle temperatures between minus 22 degrees Fahrenheit and 180 degrees Fahrenheit, while in operational temperatures between minus 40 Fahrenheit and 203 Fahrenheit during non-operation. With special aerodynamic technology in the magnetic slider, the drive series can understand altitudes up to 18,536 ft higher than any city in the world, while in operation and can handle up to 3 GB, 29.4 ms2 vibration tolerance during operation. This is the picture of a Toshiba's automotive HDD image courtesy of Toshiba's. Mm. The full spec- specifications for this drive are given in table 1. Flash memory stores data as an electrons in an isolated region on a special transistor that is built upon a silicon wafer. This type of memory is growing in popularity for many consumer devices as the storage capacity increases and the price of that storage decreases. This is also the case in automobiles. In 2012, the average memory content of the car was estimated to be around US dollars 12.80, ranging from US dollars 2 for low end models to more than US dollars 100 for fully equipped luxury vehicles. The compounded annual growth rate for semiconductor memories in automotive applications is expected to expand far faster than overall growth rate for the overall memory market. Based on analyst inputs, Micron believes that the cumulative annual growth rate for the semiconductor memory in all automotive applications is 12% through 2020. Specifications for Toshiba's automotive grade HDD. Model number MQ01A D0326. Maximum capacity formatted 320 GB. Number of platters 1. Number of heads 2. Average seek time 12 ms. Interface ATA8 serial ATA 2.6. Interface transfer rate 3 GB per second. Rotational speed 4200 R minute. External dimensions W into D into H. 69.85 mm into 100.5 mm into 9.5 mm. Weight 105 grams. Temperature operating non-operating. Temperature operating minus 30 degrees Celsius to 85 degrees Celsius. Non-operating minus 40 degrees Celsius to 95 degrees Celsius. Shock resistance operating non-operating. Shock resistance operating 2940 m per second square. Non-operating 7840 by second square. 800 G. Atmosphere pressure operating minus 300 to 5650 m. Non-operating minus 300 to 12,000 m. Vibration operating 29.4 meter per second square. Non-operating 49 meter per second square. Infotainment is expected to increase by 12% annual. Memory used in the instrument cluster is estimated to grow by 15% annually. And memory in the advanced driver assistant system is targeted to grow by 20% annually. Flash memory in a car may be implemented as chips embedded on a circuit board, or it may come in the form of removable memory cards. In 2015, SanDisk announced a new suite of automotive grade NAND flash memory solutions for next generation connected cars and automotive uh, infotainment systems. SanDisk automotive storage solutions are optimized for a wide range of in-vehicle applications, including three-dimensional mapping and advanced augmented reality in navigation systems, entertainment systems, technology, data event recorders, and more. Figure 3 shows the SanDisk automotive grade flash memory card. The SanDisk automotive portfolio of storage solutions includes an automotive grade SanDisk SD card and an iNAND embedded flash drive (EFT), which are available to automotive manufacturers in capacities up to 64 GB. The following are specifications for the SanDisk automotive solutions up to 64 GB. 64 GB SanDisk picture is shown here, figure 3. Working temperature from minus 40 degrees Celsius to 85 degrees Celsius. Enhanced power immunity up to two user partitions meet AEC Q100 specifications. The SanDisk automotive iNAND. Okay. Okay. Next. Next slide is of DFT provides eMMC 4.51 HS200 specification up to 30 sequential write up to 120 Mbps per second. Sequential read in addition to conventional flash memory, other non-volatile storage, solid state storage technologies are finding their way in automobiles. Okay. Everspin, a pioneer in MRAM, announced availability of two new additions. Means two new additions to its high-performance MRAM automotive product line. The 16 MB MRAM is available in the automotive temperature range of minus 40 degrees Celsius to 125 degrees Celsius and comes in both 8 and 16 input output configurations with fast 45 NSV and rate cycle times in parallel static RAM like interface. The 16 MB automotive MRAM use designers a high experience and high reliability precedent memory solution for the demands of the rapidly growing market. Everspin is also introducing a new 128 KB serial peripheral interface SPIM RAM in both the grade 1 minus 40 degrees Celsius to 125 degrees Celsius. A grade 3 minus 40 degrees Celsius to 85 degrees Celsius ranges. The serial interface MRAM fits in a low pin conjugal flat pack DFP package with 8 pins. It offers the same benefits as the SPI MRAM high speed writes, unlimited endurance, and high reliability, but in a small footprint. Both of these products outcome other non-volatile memory such as NAND flash memory, offering and are ideal for the increasing demand for the extensive data recording and processing in today's automotive electronic systems. Able to provide information on the Everspin MRAM automobile products. Show Micron. Okay. Wait a second. Shows Micron estimates for the growth of DRAM storage density in GB as well as core density in GB in automotive infotainment in automobiles through to 2018, while also showing the expectations for performance increasing and power requirements declining. Infotainment storage requirements, both in capacity and performances, are increasing to meet modern automobile requirements. That the likely adoption of 4K displays in automobiles will result in the demand for richer and higher capacity content, 3D maps, and data from inter-vehicle communications and new self-driving and possibly autonomous driving capabilities will require more storage. Increased downloaded frequency will require greater buffer capability. Figure 5 shows some expectations for the increase in raw storage capacity and actual data density with comparison through 2018. 18. This is the figure some automotive infotainment code storage sense DRAM density, core density, GP, power performance. Power power is the growing, performances is the yellow, core density is violet, and DRM density is sky blue. And this is a picture, a tear down view of BMW HBB 125. Let's look in the greater detail at the components. And the total estimated cost of these components is approximately US dollars 536 of the component cost, about 5% in the semiconductor memory and 6% in the cost of 200 GB HDD. This breakdown is shown in the figure 6. An exploded view of digital radio mobile module is shown in the figure 7. This is the figure 7. Okay. This is a block diagram, motherboard. This is our the ports. The summary: without the digital storage and memory components in the modern automotive electronic systems, these systems would not work. Means multiple rich media streams shown on the multiple displays and multiple audio streams require memory and storage to buffer and store the content. Okay, the memory requirements for the automobiles will continue to grow as this formerly mechanical systems become increasingly electronic and automated. The last slide. Thank you.